The rocket on the launch pad had already decided what India could not build. Long before the countdown began, one machine had quietly imposed the limits of an entire mission. The Polar Satellite Launch Vehicle was dependable, affordable, and proven. It was also too small to send a conventional spacecraft directly toward Mars. That single fact forced every later decision. Before engineers selected scientific instruments, before they routed fuel lines or wrote flight software, the spacecraft already had to become lighter than anyone would normally choose for a journey to another planet. A sheet filled with weight allocations sat near the center of those decisions. Every kilogram demanded a reason to exist. Adding one system meant removing another. There was no hidden reserve waiting to absorb mistakes. So the engineering team reached for what already worked. Hardware developed for earlier satellite missions became the foundation. Proven structures stayed. Reliable propulsion components stayed. Experimental additions disappeared before they ever reached the drawing board. Mangalyaan slowly took shape. Not by accumulating capability, but by shedding everything that could not justify its mass. At first glance, it almost looked too modest for the task ahead. The scientific payload weighed only about 15 kilograms, less than an ordinary carry-on suitcase. 5 compact instruments would have to represent the mission's scientific ambitions, while most of the spacecraft's launch weight belonged to something far less glamorous: fuel. More than 800 kilograms of propellant occupied the spacecraft because velocity, not laboratory equipment, had become the most valuable resource on board. The mass budget kept leaning toward propulsion until the vehicle resembled a machine built primarily to move itself rather than observe Mars. That choice would soon define the mission. When the rocket lifted away from Sriharikota, it performed exactly as expected, yet its success revealed another limitation almost immediately. Instead of racing directly into interplanetary space, the spacecraft settled into a long, elliptical orbit around Earth. For many missions, launch begins the journey. Here, launch only placed the spacecraft where it could start earning enough speed to leave home. Each time it returned close to Earth, its engine fired again. Every burn stretched the orbit farther outward. Earth became part launch platform, part slingshot, part training ground. Velocity was gathered one orbit at a time instead of being delivered all at once. The trajectory diagrams kept expanding. So did the risk. Every additional orbit demanded another precise engine firing. Every correction depended on fuel that could never be replaced. A single mistake would not simply delay the mission, it could erase the carefully balanced mathematics that made the entire strategy possible. Then, one graph refused to follow the plan. During the 4th orbit-raising maneuver, the main engine failed to produce the expected performance. Controllers watched the projected orbit fall short. The spacecraft was still healthy. The engine had fired, but the climb toward its intended altitude stopped too early. For a few moments, the mission no longer had the trajectory it had been built around. Telemetry pointed to a flow issue during the burn. Engineers calculated what had been lost, studied the hardware they still had, and prepared a recovery maneuver. The following day, another firing restored the missing energy. The path toward Mars reopened. The interruption was brief. Its consequences stayed with the mission. Every earlier decision to simplify now carried additional weight. There were no extravagant margins hidden elsewhere inside the spacecraft. Recovery depended on understanding the machine already flying, not replacing it with something better. Eventually, the repeated Earth orbits achieved their purpose. The spacecraft fired its engine for more than 10 minutes, gaining the final burst of speed needed to escape Earth's gravity. It slipped away into a journey that would last nearly 10 months. Then the engine went quiet. The same engine that had sent the spacecraft toward Mars would remain inactive for roughly 298 days. That sounds ordinary until you remember what liquid rocket engines endure. Propellant lines face enormous temperature swings. Valves remain motionless for months. Components built to operate together must survive nearly a year without proving they still can. No engineer on Earth could repair a valve if it stuck shut. No technician could replace a seal. The engine simply waited. As Mars slowly grew larger through the spacecraft's cameras, one final uncertainty remained. Before trusting the engine with the most important burn of the mission, controllers commanded a brief test firing. Just a few seconds. Enough to answer one question. Was the engine still alive? It responded exactly as commanded. That tiny burst lasted only moments, yet it turned months of uncertainty into cautious confidence. The spacecraft adjusted its course and continued toward the planet that had remained little more than a moving point of light for most of the journey. Then Mars itself became an obstacle. To enter orbit, the spacecraft had to fire its engine while passing behind the planet. During that period, radio signals between Earth and the spacecraft disappeared completely. More than 12 minutes of communication delay already prevented real-time control. Once Mars blocked the signal altogether, even confirmation vanished. Control rooms filled with people. Computer displays held only silence. The spacecraft was alone. Its onboard computer executed commands written months earlier. The main engine ignited. Smaller thrusters helped maintain orientation. Fuel disappeared as planned while the spacecraft remained hidden beyond the edge of another world. Nothing reached Earth. Not yet. Ground stations continued listening. The antennas stayed locked on the sky, waiting for a signal that would reveal whether every earlier compromise had been enough. Eventually, the transmission returned. The spacecraft had entered orbit around Mars. On its first attempt. The same weight allocation sheet that once represented restriction now described the path that made the achievement possible. The missing scientific instruments had become additional propellant. The smaller spacecraft had matched the limits of the available rocket. The repeated Earth orbits had replaced a launch vehicle the mission never possessed. The engine, borrowed from proven satellite technology, had survived months of silence before performing its longest and most important burn. The numbers themselves had never changed. 1,337 kilograms at launch. Roughly 15 kilograms of scientific instruments. A mission built by removing more than adding. Long after the celebration ended, that mass budget remained a page of engineering calculations describing how a spacecraft too small for a conventional Mars mission reached Mars anyway.